We have seen in human and animal growth the effects of retardation. In the cephalocaudal growth from the head downwards to the limbs, we see that the limbs eventually grow longer, even though they develop later. In the case of the disto-proximal growth, we see that the upper arm, and in the case of the legs, the upper part of the leg, grows longer and more massive, even though it starts its growth later. We see the effect of retardation in the fact that the latecomers develop larger. This is what Stephen Jay Gould called hypermorphosis, the growing beyond what might be expected. McNamara calls it paramorphosis. He speaks of pedomorphosis and paramorphosis. I'll be using the term hypomorphosis. If we look at the human being compared to old world monkeys and anthropoid ape species, we see that in the human fetus in the upper right, the hands and feet are quite a bit smaller than in the other species. And we notice in the lower drawings showing adults that the legs of the human are substantially longer. As I said earlier, the length of the human legs are famous among animal species. Look at the series of legs. We do notice in the first two drawings of the gibbon and orangutan that the arms in the adults are very long. This is regarded as the result of adaptation through natural selection to their arboreal way of life. And so a quite different principle is involved. We can now go on to look at the human hand. In the upper left of this drawing, we see that the fetal macaque hand and the embryo human hand have a remarkable similarity. If we now look at the lower row of drawings, we see that the macaque, gibbon, orangutan, chimpanzee, and the human. What is noticeable here for us is that the thumbs of the first four do not reach up as far as the base of the fingers, whereas the human thumb does reach above the base. This gives the human hand the capability of achieving the so-called precision grip. The chimpanzee gets close to the precision grip. It can do the so-called power grip, as in when we use a screwdriver. But the precision grip needs the thumb to be further up for it to be fully achieved. The chimpanzee can grasp an object and possibly use it as a tool with a thumb pressed against the side of the forefinger in this way, or the thumb pressed against the fingers like this, or by pressing the thumb against the palm. But for the full precision grip, the thumb needs to contact the tips of the fingers. We can look at the hands of two prosimians and 3 New World monkeys. We can see in the first 4 that the thumb does reach beyond the base of the fingers. But even though this does theoretically reach far enough to enact the precision grip, they cannot do so because the rotation of their thumbs is not developed. In the series of anthropoid apes, the thumb's ability to rotate increases more and more as they draw closer to the human being. This allows the precision grip to take place fully. But in these New World monkeys, they do not have the rotation of the thumb that's necessary. As an aside, we know that the spider monkey has lost its thumb due to adaptation to its arboreal way of life, swinging from limb to limb, even using its tail as a prehensile organ. We then can look at the feet. Here we see, first of all, that the fetal forms of the macaque and human are almost identical with their original primal form. That in this picture we see the feet of the howler monkey and the human. The center pictures are at their embryonic stage, and the outer two are the adult forms. The embryonic forms are very similar to each other, but the adult monkey's toes have grown very long and become finger-like, whereas the human toes have retained their original proportions. In addition, the human big toe has become enlarged and more massive. Take a look at your own toe and you'll see that this is so. It has undergone hypomorphosis. In our next picture, we see the photograph of a chimpanzee's hand and feet. I find this photo very striking with its atrophied thumb. In the last picture, we see the feet of 5 monkeys and the human. What is important for us here is to notice the proportion of the toes to the big toe in the first 5 compared to the human proportions. We see also that the big toes of the first 5 slant away from the rest of the foot, somewhat like a thumb would do. And also very noticeable is the hypermorphic growth of the big toe and the heel, both of which were essential for that specifically human characteristic of upright stance. So we have seen the effects of hypermorphosis in parts of the body that are latecomers in their growth, such as the late-growing legs and arms, the upper parts of human legs and arms, the thumb, and the big toe and heel. Hypermorphosis, along with pedomorphosis, plays its part in both the cephalocaudal and the distoproximal patterns of growth in humans and other primates.